All right, so you've got the notes for section 5.1 and 5.2. So we'll start here on 5.2, estimating population proportion. So this unit deals with making estimates and sample sizes, or making estimates for a population based off of a sample, essentially. So you have a point estimate. So the sample proportion, denoted by P with a little hat over the top of it, is the best point estimate of the population proportion. We'll talk about confidence intervals. So you can use the sample proportion to construct a confidence interval to estimate the true value of a population proportion. We should know how to construct and interpret a confidence interval, and then sample size, how to find the sample size necessary to estimate, to make our estimation mostly accurate. So down here it says, so a point estimate is a single value or point used to approximate a population parameter. So the Pew Research Center conducted a survey of 1,007 adults and found that 85% of them know what Twitter is. Based on that result, find the best point estimate of the proportion of all adults who know what Twitter is. Well, what's saying up here is a point estimate, approximated population parameter. So we did a sample of 1,000 or so adults and found that 85% of them. So that 85% is our point estimate. Now, since this is a proportion, it's 0.85 because you have to divide by 100 to make it back into a proportion. Okay, so confidence intervals is a range or an interval of values used to estimate the true value of a population parameter. A confidence interval is sometimes abbreviated CI. So the confidence level is the probability 1 minus alpha, so it says 0.95 or 95%, that the confidence interval actually does contain the population parameter, assuming the estimation process is repeated a large number of times. The confidence level is sometimes also called the degree of confidence or the confidence coefficient. So here's our most common values. So you can be 90% confident, 95% confident, 99% confident, and their corresponding alpha values. If you notice, alpha plus that number always adds up to 1. So you have to be careful, though, with what a confidence interval means. We are 95%, so this is the correct way to interpret it. Now we are 95% confident the interval actually does contain the true value of the population proportion. It's not correct to say there's a 95% chance the true value of P will fall in the interval. That's because that value P is a number. You could calculate it if you wanted to, so there's not a probability, there's not a chance that it falls in the number because it can't change its value. What it actually is talking about is, so confidence level 95% tells us the process we're using will in the long run result in a confidence interval limits that contain the true proportion 95% of the time. So if we repeat our process over and over again, and we look at our least and greatest, least and greatest, least and greatest, we know the smallest P can be the largest P can be. 95% of the time we will have the actual value in between our two endpoints. That's what that is, and if you have to do it a lot of times. So it's not a percent chance of it happening once. So you can use confident intervals to compare different data sets, but you have to be careful with how you do that. So that's just a comment used for making formal and final conclusions. Okay, so using confidence intervals, we're making an informal judgment. We're not doing quite the math yet for a formal judgment. Okay, so critical values. Critical values are based on the following observations. Under certain conditions, a sampling distribution of a sample proportions can be approximated by a normal distribution. A z-score associated with the sample proportion has a probability of alpha over 2 of falling in the right tail. Z-score separating the right tail region is denoted by z alpha over 2. Remember, alpha is above. It is referred to as a critical value because it is on the borderline separating z-scores from a sample population that are likely to occur from those that are unlikely to occur. So down here, critical value is the number on the borderline separating sample statistics that are likely to occur from those that are unlikely. The number z alpha over 2 is a critical value that is a z-score with the property that separates an area of alpha over 2 in the right tail of the standard normal distribution. Okay, so example 2, find the critical value z alpha over 2 that corresponds to a 95% confidence interval. So for this problem, our alpha is 1 minus that. So our alpha value is 0.05, which means alpha over 2 is 0.025. So that means we need some value that has, we need a z-score that has 0.025 above it. So which means on our table, since we always have less thans, we're looking for the z-score that corresponds to 1 minus that, or 0.975. So for this problem, I have to go to my handy dandy table and find 0.975. 0.975 right there. So that row is 1.9 and going up is 0.06, so 1.96. Now there is another way to do this without having to do the 1 minus step, is that you look for that number in the table, 0.025, and then take its opposite, because if you do 0.025, that's going to be negative 1.96. Negative 1.9. So there's your 0.025. But the z critical values are always positive, so you take the opposite value. So you could flip it around without having to do the 1 minus step. So here's just a table summarizing them. So your confidence level, your alpha value, and the critical value that goes with it. So z alpha over 2. So now remember to find this, so this is the one we just did here, 95%. So alpha is 0.05, half of that is 0.025, and we looked up that number here. So for 90%, that's 0.1 for alpha, half of 0.1 is 0.05, so you'd find this number by looking up 0.05 or 0.95. This one, 0.01, so we'd find it by looking up 0.005 in the table, half of that value. All right, so down here we've got the margin of error. So when data from a simple random sample are used to estimate a population proportion, the margin of error denoted by E is the maximum likely difference between the observed sample proportion and the true value of the population. It's called the maximum error of the estimate. It can be found by multiplying the critical value by the standard deviation of the sample proportions, which is what this square rooty stuff is. So p hat and q hat are the sample proportions and is the number of values that you have. On this page, we talk about how to construct a confidence interval. So p is the population proportion, p hat is your sample proportion. So you take a smaller group out of the entire population and measure their proportion. N is the number in your group. E is the margin of error. We talked about z alpha over 2 already. So here's actually how you construct it mathematically. So we need to calculate the error value first using this formula. And then our proportion is somewhere between p hat minus the error and p hat plus the error. So that it could be, our error tells us how far up or how far down our values can go. Sometimes you'll see it written like this, or as an interval written like that. Round the confidence interval limits for p to 3 significant digits. So depending on your measurement, you'll have different things. Okay, so here's our procedure. So procedure constructing, so use the table of z-scores to find the critical value, either from your notes or look it up in the actual full z-score table, calculate margin of error, and then using that and this formula to construct your values. All right, so example 3. In example 1, we know that Pew Research Center poll of 1,007 randomly selected adults showed that 85% of the correspondents knew what Twitter was. Those sample results are, so there's your N, there's your P. Find the margin of error. So to find margin of error, we need this formula. Square root P hat, Q hat over N. So let's jot down what our numbers are. So Z alpha over 2, so we're doing 95% confidence level. So from our table back on page 4, 95% confidence, that's 1.96. P hat is given to us in the problem, that's 0.85, which means Q hat, if 85% do know what it is, 15% don't, and N is 1,007. And we would just fill those numbers into my formula. So E equals 1.96 square root of 0.85 times 0.15 divided by 1,007. And then that just goes in our calculator. So 0.85 times 0.15 divided by 1,007, the square root of that number times 0.196 is 0.0221. So that's our error. Find the confidence interval. So P is less than, so it's gonna look like this. So this is this formula right here. So P hat plus the value goes up here. So 0.85 plus 0.0221. That's 0.8721. And p hat minus 0.0221 is 0.8279. So based on the results, can we safely say, conclude that more than 75% of adults know what Twitter is? So because our confidence interval ranges between 0.8279 and 0.8721, which is 83% to 87%, we can say that that is an accurate statement to make, because even at our lowest end, it is more than 75%. So, yes. Because the values are going to fall, they're likely to fall between this range, and this range is always more than 75%. So this, describes results and all relevant information. So, between 83% and, oops, off the screen, 87% of adults, oops, capital T, Twitter is, based off a survey of 1,007 adults. So something like that would be a conclusion statement. Okay, we can also go backwards and figure out how many people we need to survey if we want to be that confident. So here's our formulas for n. So these are actually just rearrangements of the error formula from before. If you actually solve it out for n, you'd get this. You have to move everything over, fun stuff. So z alpha over 2 squared, p hat q hat over e squared. That's if you know an estimate for p hat. And if you don't, you just assume that that product is 0.25. All right. So if the computer sample size n is not a whole number, round the value of n up to the next larger whole number. So the regular rounding rules do not apply. If you get 2.1, that rounds all the way up to 3 because you want the minimum value. So you can't have 2.1 people, so the fewest people you can have are 3. Can't go down to 2 because that's not actually enough. You have to go always round up. All right, so example 4, Gap Banana Republic J. Crew. How many adults must be surveyed in order to be 95% confident that the sample percentage is in error by no more than 3 percentage points? So this value here is our p hat 0.66, which means q hat for this problem is 0.34. We're solving for n. Our z alpha for 2 values, the 1.96 again, which is the same confidence as before. And we're just going to fill in 3 percentage points, so that's 0.03 for the error. You have to convert your 3% into a percentage point. So we'll fill in our formula. So n is equal to z alpha over 2 squared times p hat times q hat all over e squared. And that's all numbers, so that all just goes in your calculator. 1.96 squared times 0.66 times 0.34 divided by 0.03 squared. And as a calculator, you get 957.8. So I need to round up, so I'd have to survey 958 people to be sure that my measurement was accurate. No prior information uses the other formula, so z alpha over 2 squared, and then just times 0.25. That's using the bottom equation here. No estimate known. Over 0.03 squared, and then this comes out to be 1.96 squared times 0.25 divided by 0.03 squared. Gives us 1067.1, so rounded up. You would have to survey slightly more people if we did not have an actual estimate to work with. So don't forget to round up. Okay, and last thing I believe we have here, finding the point estimate and E from a confidence interval. So you can actually work backwards. If you know your confidence interval, you can find your estimator and your error using these formulas. So to find the point estimate, you add your confidence intervals divided by 2. To find the margin of error, you take the difference divided by 2. So the article high-dose nicotine patch therapy includes a statement of 71 subjects, 70% were abstinent from smoking at 8 weeks, 95% confidence interval, 58% to 81%. Use the statement to find the point estimate P and the margin of error E. So the point estimate P hat is going to be the upper confidence, which is 0.01, plus the lower, 0.58, divided by 2. 0.01 plus 0.58, divided by 2, 0.695 would be your answer. So that would be our about 69% of people. To find the error, we use the other one, 0.81 minus 0.58 divided by 2. So 0.81 minus 0.58 divided by 2, that's 0.115. So this value is the value essentially that lies at the center of our confidence interval, and the high and low differ by that much. If you take 0.115 and add it to this, you'll get your 81. If you take 69.5% minus 11.5%, you'll get your 58%. But that brings us to the end of the section.